Welcome to Chapter 17, Natural Language Processing. In this chapter, we explore how machine learning reads, interprets, and works with human language through concepts, methods, Python practice, and case studies. Think about how much of your day runs on text. Natural language processing, usually shortened to NLP, is the branch of machine learning that handles this messy, wonderful data. And here we build up the toolkit that tames it. By the end of this chapter, you should be able to explain what NLP is and why text is hard for computers, recognize common applications, and carry out the standard pre-processing steps, from tokenization and stop word removal to stemming and lemmatization. You should also be able to represent text numerically with bag of words and TF-IDF. Describe the intuition behind word and document embeddings, train and evaluate a text classifier in Python, and explain sentiment analysis and topic modeling. This figure shows a classical NLP preprocessing pipeline. Raw text is first cleaned and normalized, then turned into features such as TF-IDF vectors, which are finally passed to a classifier. So, what is natural language processing? It is the field that builds methods for computers to read, interpret, generate, and respond to human language, whether that language arrives as written text or as transcribed speech. NLP covers a wide range of tasks: sorting messages with text classification, judging opinions with sentiment analysis, discovering themes through topic modeling, pulling out names and dates, plus translation, question answering, chatbots, and text generation. What makes all of this genuinely difficult is that human language is ambiguous and deeply context dependent, so the same words can mean different things in different situations. Most of the data sets we have used so far in this book are structured. Text is different. When a review says the delivery was fast, but the product quality was poor, a human reads it instantly. Shipping good, item bad, overall unhappy. NLP shows up everywhere, analyzing reviews and surveys, detecting spam and phishing, searching legal and medical documents, screening resumes, routing support tickets, classifying news, and powering search engines, voice assistants, and large language models. To make this concrete, let us picture three organizations and how each one might put these tools to work. Text preprocessing follows a sequence of steps: lowercasing, removing punctuation and numbers when uninformative, tokenization, removing stop words, stemming or lemmatization, and finally converting the clean tokens into numerical features. A word of caution: more cleaning is not always better. Each step throws something away, so we should keep only the transformations that genuinely help the task at hand. Tokenization splits a string into smaller units called tokens. It is one of the very first steps in almost every NLP pipeline, and the strategy you choose shapes everything downstream. Stop words are the high-frequency glue words of a language, like the, is, and, of, to, and in. Because they appear nearly everywhere, they often add little for tasks like topic classification, though removing them is a judgment call, not a law. Stemming and lemmatization both collapse related word forms to a single representative so that run, running, and ran do not waste three separate slots in your vocabulary. Stemming chops words to a rough base using simple rules. Here we see stemming in action. Running becomes run, studies becomes study, and connected becomes connect. Notice that the result is not always a real word. Lemmatization is the more careful cousin of stemming. It uses a dictionary and grammar to find a word's true base form. With lemmatization, running becomes run, better becomes good, and studies becomes study. The outputs are always genuine words, and even irregular forms are handled correctly. Lemmatization produces cleaner, real words and handles irregular cases like better becoming good, but it costs more computation than simple stemming. The simplest way to turn text into numbers is to ignore word order entirely and just count words. This is the bag of words idea. Consider three short documents. I love this product, I hate this product, and this product is useful. We will represent each one numerically. We build a vocabulary from all the words that appear across the documents, and then we simply count how many times each word occurs in each document. Here is the resulting bag of words table. Each row is a document and each column is a vocabulary word, with the entries holding the counts. Each document is now a row of numbers, which is exactly the kind of input a classifier understands. We have turned language into data. Bag of words treats every word as equally important, which is rarely true. TF-IDF fixes this by combining two ideas. Term frequency rewards words frequent within a document, while inverse document frequency penalizes words common across all documents. Multiply the two together, and you get a score that is high for words frequent in one document but rare across the collection, and low for ubiquitous words like this or product. TF-IDF is a true workhorse of classical NLP. The promise of TF-IDF, that it lifts distinctive words and crushes ubiquitous ones, is easy to verify on a tiny corpus. Take 3 reviews whose vocabulary is great: phone, value, slow, and broke. First, we tally how often each word appears in each document, its term frequency, and in how many documents it appears at all, its document frequency. This table records the term counts per document together with the document frequency of each word across our small corpus of 3 reviews. Notice that phone appears in all 3 documents, while value, slow, and broke each appear in only one. That difference is exactly what TF-IDF will exploit. Step 2 is the inverse document frequency, which rewards words that are rare across the corpus. The formula defines the IDF of a term as the logarithm base 10 of the total number of documents divided by the number of documents containing that term. Plugging in the document frequencies, phone gets an IDF of 0 because it appears everywhere. Great gets about 0.176, while value, slow, and broke each get about 0.477. In step 3, the TF-IDF score of a word in a document is simply its count in that document multiplied by its IDF. This figure shows the TF-IDF matrix for the 3 reviews, where darker cells mean higher scores and blank cells are 0. The phone column is entirely 0 because that word appears in every document. The matrix tells the whole story at a glance. Distinctive words light up, while words shared by everything fade to 0. Bag of words and TF-IDF share a blind spot. To them, car and vehicle are as unrelated as car and banana. An embedding fixes this by representing each word as a dense vector, learned so that similar words land near each other, like word to vec. Other classic methods for learning these vectors include glove and fast text. Each of these produces a single fixed vector for every word in the vocabulary. This figure illustrates word embeddings, placing each word at a point in a vector space so that words used in similar contexts, such as king and queen or car and vehicle, land near one another. Embeddings need not stop at single words. Whole documents can be embedded too, which powers similarity and clustering, semantic search by meaning rather than keyword, recommendation, deduplication, and the retrieval augmented generation we cover in Chapter 18. Text classification assigns predefined categories to documents, and it is the most common NLP task you will build in practice. Typical examples include spam versus legitimate email, positive versus negative reviews, classifying news by topic, and routing support tickets or triaging documents to the right place. A traditional pipeline follows a clean recipe you will recognize from the supervised skeleton in Chapter 1. Collect labeled text, clean and pre-process it. Convert it to features with bag of words or TF-IDF, train a classifier, and evaluate it. Let us look at the end-to-end flow from a raw document all the way to a predicted label. This figure traces a text classification pipeline. Raw text is cleaned, converted into numerical features, and passed to a trained classifier that finally outputs a label. Naive Bayes is the classic first choice for text. It assumes the words are independent given the class, which is obviously false since words travel in groups, yet it still works remarkably well on text. Sentiment analysis is text classification with a specific target. The emotional tone or opinion in a piece of text, usually labeled positive, negative, or neutral. For example, the product is excellent reads as positive, the service was terrible reads as negative, and the package arrived yesterday is simply neutral. Businesses lean on sentiment analysis heavily, using it for review analysis, social media monitoring, satisfaction tracking, and managing brand reputation. The tasks so far have been supervised, where you bring labeled examples. Topic modeling is different, it is unsupervised, and the standard tool is latent Dirichlet allocation, or LDA. Topic modeling answers questions like what themes dominate our customer complaints, what subjects do these news articles cluster around, and what concerns recur across thousands of survey responses. One honest caveat: the output is a set of word lists, not tidy labels. It is up to us to read each list and decide what theme it represents. Bag of words throws away order, but order is often where the meaning lives. The movie was not boring at all, and the movie was boring. Share almost every word, yet say opposite things. Sequence models capture that order. Transformers changed NLP by replacing sequential reading with attention, a mechanism that lets every token look directly at every other token, no matter how far apart. They are the foundation of essentially all modern NLP, including today's large language models. Here is the key point. There are two eras of NLP, and both still matter. Classical methods like TF-IDF with logistic regression are fast and interpretable, while transformers capture deeper meaning at higher cost. Reach for the simple tool first. How you measure an NLP system depends entirely on the task at hand. For classification, common metrics include accuracy, the share of correct predictions, precision and recall, which matter most when the classes are imbalanced, and the F1 score, which balances precision and recall. For information retrieval and search, the question shifts to whether the right items appear near the top, so we use metrics like precision at K, recall at K, and mean reciprocal rank. NLP systems increasingly stand between people and consequential decisions in hiring, lending, healthcare, and content moderation. That raises real risks: absorbed bias, harmful outputs, privacy leakage, misclassification of sensitive content, and over-reliance without human review. The root issue is that language data reflects the society that produced it, including its prejudices. A model trained on such data can quietly inherit and amplify those biases. Now, let us put this into practice. If you have the datasets library from Hugging Face installed, the snippet ahead pulls the AG News collection directly so we can classify it. This code loads the AG News dataset of 4 news topics, takes a manageable training slice so it runs quickly on a laptop, and builds a single pipeline that combines TF-IDF features with logistic regression. The flow here mirrors the supervised recipe from earlier in the chapter, and if you prefer a dataset with no external download, scikit-learn's built-in 20 news groups works with the very same pipeline. You just swap the loading lines. Sentiment analysis uses the very same machinery as before, simply pointed at a different target. This code loads the IMDb movie review dataset, samples training and test slices, and trains a TF-IDF and logistic regression pipeline, then prints a classification report comparing the predicted sentiment against the true labels. Notice that this time we deliberately did not remove English stop words. For sentiment, small words like not and very can flip the meaning, so we keep them. Classical TF-IDF is a strong baseline, but sometimes you want the depth of a transformer without training one yourself. This code uses a ready-made Hugging Face pipeline that downloads a small pre-trained sentiment model on first run, then classifies a few example reviews and prints each predicted label with its confidence score. Notice what is missing here. No feature engineering, no TF-IDF, and no training loop. The pre-trained model does all the heavy lifting for us. This code applies topic modeling with LDA. It vectorizes a collection of documents into word counts, fits a model with 6 topics, and then prints the top 10 words for each topic it discovers. Consider this case study. A mid-sized online retailer collects tens of thousands of product reviews every month. Buried in that text is exactly the feedback the teams need, but no one can read it all by hand. The team designs a two-stage workflow that uses both halves of this chapter. First, classify reviews by sentiment, then run a topic model over the negative ones to discover what keeps going wrong. The discipline around it ties back to the whole book. The following code reproduces the multi-topic classification at the heart of the case study, routing incoming text into one of 4 subject areas using TF-IDF features and naive Bayes. This code loads 4 newsgroup categories that mirror the routing scenario, makes a simple 80-20 split, and prepares a TF-IDF and naive Bayes pipeline with bigrams to separate the topics. Strong per-class F1 scores confirm that TF-IDF bigrams combined with naive Bayes can reliably separate the topic areas, which is exactly the automated routing the retailer needed before any human steps in. To summarize, we built up text representations in stages, from the order-blind counts of bag of words to the distinctiveness weighting of TF-IDF to embeddings that place meaning in geometric space. For further reading, Bishop offers a rigorous treatment of probabilistic classifiers. Pedregosa and colleagues describe scikit-learn, and the Hugging Face, NLTK, and SpaceEye documentation cover pre-trained pipelines and classical pre-processing tools. That brings us to the end of Chapter 17 on natural language processing, where we learn to turn raw text into features, classifiers, and insight.